here. And it was I heard there was a homecoming game yesterday, so it's always a fun night out. It's great to be back. I'm actually from Illinois, from Southern Illinois, from Melville, so when I get back to the campus here, I've had many friends who attend UIC. It's always nice to return back to the roots somehow. So as you probably saw from my bio that's out there, I'm from IBM Research. This is actually quite loud, is it? Can you just turn down a little? Also, I have a lot of echo going on. This is going to help wake you up in the morning. Testing. How's this? Can you hear me still? Nope. No. Testing. Can you hear me back there without me using a mic? Is this being recorded? Do you need a mic?
Yeah.
Okay. So let me just. I talk a little faster in this thing, so it's no problem. So as you saw from my bio out there, I'm from IBM, which is not a startup. It's been around for I think 107 years. Although what I'm talking to you about today is a bit of a startup. I had a recent job title change called, so I'm Director of Learning Health Systems. I'll talk a little about that. And another big change that I'll talk about is our focus on research AI, which is the track that we're in here. So for those of you who don't know, IBM Research is a separate business unit within IBM. It's actually one of the smaller business units. We've been around since 1945, working on research across a broad number of areas. We've had quite a bit of success, 6 Nobel laureates, 6 Turing Awards, a number of medals in science, relevant technology. And probably our biggest accomplishment is this next slide here. Next slide. Oops. Okay, so this is just continue. Let's stop there. So our biggest accomplishment is we do a lot of patents. We have over 8,000 patents per year. We're by far the largest lead, and many of these patents are in the area of AI and also in the area of healthcare. That's the main big focus right now. So you can imagine we're very productive in that sense. We also publish and present what I'm doing today, but our goal is to really be able to generate innovative ideas and really ensure we can change the marketplace. So in IBM Research, unlike other research units with other companies, we really have a broad range of topic areas. It's almost like a university with multiple departments, everything from the basic sciences, chemistry, biology, and physics, to applied sciences like behavioral science, computational biology, and so forth. So we have researchers in different areas. Hopefully. It's trying to connect to the Wi-Fi and then it's stopping to do it moving forward. And we also work in multiple different industries and research. So we don't work just within IBM, but we also work with companies outside of IBM, directly with the kind of data they have in healthcare, in aviation, and so forth. So it's a pretty complex set of activities that are going on here, which creates a wide range of research opportunities for us. The other exciting thing is that we're a global lab. We have currently 12 labs around the globe, including all continents except Antarctica. Probably don't have one Antarctica anytime soon, but in each of these areas we have a focus that's specific to that location. So, for example, in Brazil, we're working with the oil and gas industry there, thinking about how to apply AI to their problems of looking for large amounts of data, deciding where to utilize resources. In Austin, we're focused on aging and accessibility. In Africa, we're focused on healthcare there, not just infectious diseases, but also chronic diseases, which are becoming more of an issue. within Africa. In Australia, we work in financial services. So we have a wide variety of activities across here trying to meet the local needs of the globe. And I'm proud to announce that we just last week launched our own lab here in Cambridge in the Independent Lab. So it's actually the 13th new lab with a focus on AI. So we're collaborating primarily with MIT, where we have a put investment of $240 million with them to be able to look at next generation of AI. But we're also working in what's called the Cognitive Research Network, including schools like UIC, to fund individual labs in specific areas of AI research. So this is the team that I have there. And some of these faces look familiar. Shreya, who's here in the front. I came on campus last October, and I'll be back actually October 25th of this year to go ahead and recruit our staff for this year. A wide variety of people working in different areas: mobile health, cloud computing, network science, and epidemiology. Who've been working with data scientists and researching there. So great team of people to have. So what I want to focus on today is just talking about some of the new initiatives, strategic initiatives that we have that largely encompass AI and infrastructure. And so I'm going to talk about some of the core AI stuff we're developing that we're trying to make breakthroughs in. I'm going to talk about an area called blockchain. How many of you have heard of blockchain before? Okay, quite a few. So you'll understand. We'll talk about how AI works with that. Talk about how we're using science and research that we're doing and AI to transform industries. And then most fundamentally, the stuff that we're doing with big data and AI just is not going to work with traditional computer architecture. So we have to really think about the next generation of computing and how we're going to be able to scale up the algorithms that we have and the data we have. So in each of these areas, we have some interesting projects going on. In the core AI, we're trying to do a lot of work in visual understanding that goes from everything from medical imaging, trying to detect tumors and medical images, to videos now that we're working on. We're working on blockchain to be able to rapidly launch this into industry. It's a huge demand in industry right now for use of blockchain. Through science and AI, we're working things like dealing with large amounts of data from genomics, trying to help cancer researchers and clinicians be able to understand when a patient comes in, which genes are most relevant to their treatment options, and talk a little bit about the different types of new technology we're working on in computing. So, AI is, as you probably know, is the big hot topic right now in computer science. I don't know how it is here. What's the introductory class here for machine learning? 440? Yeah. And how many students are in 440?
This semester, 500.
500. Okay. So it's probably the same trends that we see everywhere. At MIT and Stanford, from data we have collected from them, the number of students coming into classes doubles within 5 years. So intro to machine learning class. So this is something that people are very interested in and want to understand, and really, I think, fundamental to how we're going to move forward in computing. So the areas that we've been working on are largely around signal comprehension, so taking images and videos and being able to understand what is inside this. So Microsoft provides a set of images that are annotated called COCO, and if you're interested in image analysis, you can use these. So we can start looking at images and be able to create comprehension, like being able to find out this is actually a bird sitting in a bowl splashing around, right? Trying to figure out what is the parts of this image here that can help us reveal that. So a lot of these images are animals largely for protection, but these are things we're actually able to start doing in other settings, trying to do image analysis. With some of the work we're doing in videos, we're taking the videos and breaking them into 3-second segments and then being able to annotate those and then creating a new corpus of videos that are small bits and then be able to tell a story through the videos. We've been working on linear reasoning for quite a number of years, and our current kind of effort is looking at how we can create computers that can debate us, can engage us and start interacting with us as humans to be able to tell us permission has, provide evidence, and then take evidence that we have to get back to try to reason with that. And then we're also very interested in looking at interaction of humans with computers. We have an area here that is in looking at applying this into psychiatry. So in psychiatry, we deal with issues of people's mental health. We found that by looking at the sentence structure of how people speak, we can determine what type of mental health conditions they have. We can look at the number of phrases they use as a way of determining whether they might have some mental health problems in the future. And here with Parkinson's disease, we can tell from the pressure of the speech that the person has whether how far advanced Parkinson's disease is. So using speech in itself provides us a large number of ways of looking at how well people are doing. So the next part I want to talk about is blockchain here. So blockchain is, as you may know, came out of the Bitcoin kind of algorithms. And I'll talk to you, Bitcoin is a public ledger. Basically, if you have currency, cryptocurrency on Bitcoin, everybody can see how much money you have. And as you do transactions on that, you can ensure that the transactions maintain the value of your Bitcoin. So there's a way to ensure that no one's hacking the system, basically speaking. And one can create more Bitcoins by using algorithms to mine that create complexity in the system to create more Bitcoins. So this has largely been around for a number of years now. Bitcoin is considered to be eventually kind of on the downside. There's another alternative called Ethereum that people are using as an alternative to Bitcoin. And as you can imagine, the financial industry is very interested in the whole idea of cryptocurrencies. But the idea of having a ledger that's shared and secure is something that is not just for cryptocurrencies. We've been working with Maersk, which is a shipping company, to understand how they do the transactions and whether the idea of keeping the transactions like you would with currency would make sense. So we did a study with Maersk. Maersk, one example, shipped flowers from East Africa, tulips, to the Netherlands. The Netherlands, as you may know, thinks they grow some tulips, but a large amount of the tulips they actually offer in the Netherlands actually come from Kenya. So to create this transaction of flowers being put onto a shipping crate in Kenya to someone in the Netherlands purchasing it, there has to be a series of transactions. And currently, those transactions are actually all done on paper, believe it or not. So if there's one piece of paper that's missing at some point, that can hold up the shipment for a couple of days, and if it's flowers, that's too long. So Maersk and other industries, shipping partners, have been looking at using blockchain as a way of securing information they have. So when something's put onto the blockchain here, the information is ensured that the ledger in Kenya matches the ledger in Amsterdam. So someone registers they put in a crate of flowers, then the flowers show up in Amsterdam, and the banker who's supposed to pay for the shipment decides that the flowers are on the ship, okay? And no one can hack that. So this has been incredible. This is why we've seen this industry changing rapidly, the financial industry as well, and any other industry that needs to have a way of sharing information across multiple parties. So this is basically taking out some of the friction in our economy, because most of this has been done on a very old system, requiring a lot of people in the middle of the system to be able to check everything. When you can have transactions that can be done instantaneously by a computer, which can be verified, you can speed up this transaction from a couple of days to milliseconds at this point. And this is now being thought of as ways of doing the stock changing the stock market too. In the stock market, we also have stockbrokers who verify prices. But if this could be used instead, then you can ensure that the value when you're purchasing the stock doesn't need to have a person telling you it's true or not true. You can just verify right there and buy the stock. So the entire economy could rapidly change as a process of this and save trillions of dollars as a result. So we're excited. So the way what IBM has done is work with the Linux Foundation to create its own version of blockchain called Hyperledger. And the reason that we're creating a separate blockchain is that we find that most of our transactions that we want are for things that people don't want to be public. There are a number of parties that are working together on the blockchain, but they want to keep their transactions private to themselves. That's true in the financial industry, shipping industry, and other industries. So we've worked with the Linux Foundation and a couple of other companies to create this open source Hyperledger, which is secured through a set of transactions we have. So it has a shared ledger, just like with Bitcoin. But the differences are that there's a permissioning system about who can get into who can add to the transactions and who can verify the transactions. And then there has to be consensus that something changes on the ledger. Everyone looks at it and agrees that it's okay. So some parties are actually approved, who are not actually involved in transactions, approve the transactions, but other ones are involved in transactions. And then most interesting, and I think from a computer science perspective, all this is written as a smart contract at the level of transactions. So it's actually code. The whole set of transactions is written as code so that verifies what's happening meets the standards by which the people are engaging. And as I said, it's reducing time, removing costs, it's mitigating risk, It's enabling entire business models. And this is why we're very excited about this. And IBM, other companies are very excited. Microsoft is working with Ethereum to create private hyperledgers. And something that we didn't think about even 2 or 3 years ago is something that we think will, in 5 or 6 years, will be largely adopted throughout multiple industries, including in healthcare. And so this is where using this hyperledger is to be very transformative. Right now, if you're a patient and you go to see your doctor, and your doctor records information in an electronic health record, legally, that's your information. You own that information that goes in. Technically, it's impossible to get that information out. It's impossible to use that information yourself, right? So you have no control of the information that you have when you go into the healthcare system. Everyone, this is just a disaster in terms of what you own and don't own as a person. On the other hand, you're also wearing wearable devices and information that collects information about you that you want to share with your doctor, right? So you want to bring in and say, hey, my blood pressure the last few weeks was this. Or I have type 2 diabetes, I've been checking my blood sugar, so here's the number. There's right now no way for you to provision your information to the doctor, to tell the doctor this is my information. The system is partly broken on his or her own side. The doctor's side, you can't take that information. But there's no way for you to share it and say, okay, here it is right now. You can print it out and stuff like that, or show it on your computer. So what we're interested in doing is putting the patient in the middle of all their data. The data they collect on themselves, the data that's sitting inside current health IT systems, and allowing them to be in charge of this. So a project we're working on right now is taking this and trying to understand how we consent people. So letting the patient be the owner of their data. They can allow other people to access their data, even the health system itself. So that even the health system owns their data, they can actually create the link. So as data is being collected at home, and then going over into the hospital, and there's sensitive data being collected, like genomic information, that has a lot of details about a person's health. That information can then be provisioned to their physician at the end, who then is added to the blockchain. So all the data is maintained on the blockchain. Even if the data sits in a separate health IT system, the link to that is actually maintained on the blockchain. And we think that this is going to really advance healthcare, because now, instead of a patient having information in this health system, and a watch, and some other place, all this information can come back to the patient automatically. And if they go to the emergency room, they can just add the emergency room to the blockchain and allow them to see all the transactions and all the data that sits there. So we're working on trying to make this a possibility. We've also been working with the Food and Drug Administration. They're very interested in this, as information is being collected in clinical trials and clinical studies. It gets submitted to the FDA. The FDA has to verify the source of information from those trials and studies is actually correct before it can decide to approve a drug or not approve a drug. And so they're coming up with their standards for blockchain for research. So as pharmaceutical companies, as medical researchers submit their data, all information should be put on the blockchain, and all the FDA has to do is just take a look at the blockchain and say, okay, every transaction on here has been verified and has been approved. There's been no one who's changed any data, no one's submitting data that's incorrect about this trial. It came from this individual, this patient, or the subject, it came from this use of this drug. Everything like that can be stored on the blockchain. So we started this in 2017 to try to set a standard with the FDA and to help the pharmaceutical industries and medical researchers be able to verify the information. Again, if this is done, there's no manual review. It's just automatically assessed and determined if the data is correct. Here's where the things were going on in blockchain. It's we're looking at new algorithms for cryptography. Obviously, you have to keep the cryptography as advanced as possible so the system can't get hacked. New consensus algorithms that deal with multiple parties. It's a big challenge when you have 10 plus parties who are involved. They all have to understand how their data is being managed in the blockchain. Really interesting work going on AI and blockchain. So how do you create smart contracts using AI technologies so people don't have to spend a lot of time coding the blockchain? They can just specify at a high level what they want the blockchain to do, and that automatically becomes a smart contract. And then IoT design. IoT devices adding their data to the blockchain. So we don't want all the IoT data, trillions of bits of information going on the blockchain. We want parts of it that are connected to blockchain so that we can access those parts that are important. So we're applying the AI and the blockchain, as I mentioned, to multiple industries. One of the interesting projects I have here is in China that we set up, which is called Green Horizons Project. We began about 3 years ago, 4 years ago to start this project. We started putting sensors throughout China. And as you know, in Beijing and many cities in Asia and around the world, the level of pollution is enormous. And it's very hard for governments to determine what's the source of the pollution. There's factories, there's automobiles, there's all different sources. And so the governments try different policies and strategies, and then they try to determine what happens. Obviously, they shut down all the industry. They can't get the pollution to come down as happened in Beijing during the Olympics. But that's obviously not cost effective. So we want to be able to use all this data that we're collecting around the world. And in China, we had 367 cities that have deployed these IoT sensors that link with AI. And then we have about 34 exabytes of data ingested. It's a huge amount of data. So throughout China and through the Green Horizons Project, we're able to collect all this data. 3 years ago, we were able to predict ahead of time what the weather would be within about 3 days, how much pollution the weather would be. Now, currently, we're using our AI algorithms. We can predict in 10 days in advance. So that gives time for the government to be able to give warnings, to adjust whatever they need to adjust, if they feel they have control over, to be able to change this. And this is all being done through IBM research, not through IBM company. We're working directly with the government of China to help do this. And we're now deploying the same kind of technology throughout the globe, in South America, in Africa, other places where there's high levels of pollution. One side that somebody may not know that we actually, IBM bought the Weather Channel, the weather company a couple of years ago, so we have this infrastructure already in place from the company side. So all the data that's coming in terms of weather throughout the globe is coming from this one data platform that we have control over. And so there's a nice way to control this further beyond that. In healthcare, we're using AI in a variety of ways. But one I think the most exciting ways is how we're trying to work on wiring the home and the patient themselves. So in this case, we're working with Pfizer directly from IBM Research, and we're looking at patients who have Parkinson's disease. Parkinson's disease is a problem where patients have either changes in their gait, they have tremors, or their voice changes. And it's a fairly unfortunate condition that gets worse over time. There are a number of drugs that can help people get better, and there are new drugs that are coming to the market. Particularly ones that Pfizer is creating, but other pharma is creating this too as well. Currently, when someone has Parkinson's disease and they want to get seen by a doctor, they come in and the doctor spends half an hour doing this set of tests, which gives them a score at that point. That basically looks at their gait, how they're walking, their hand, the tremors, the ability to do certain tasks. And what we found is by using wearable devices, we can capture this data more directly and continuously instead of having to go to the physician's office to do this. And so we'd like to be able to use this technology now to also monitor patients in their home. So in addition to wiring the patient, which sensors are important for the patient to detect their particular condition, we also are wiring the home. So we have a house that we designed in Yorktown Heights in New York, and a similar house that Pfizer designed in Boston, which has a bunch of sensors put in there that lets us look at how people with Parkinson's disease move around their space, how they undertake what's called activities of daily living, cooking, bathing, putting on clothes, and trying to determine how well they're able to do that. With the idea being that we can monitor the level of Parkinson's disease without the clinician right there having to do it, and give information back to the clinician about how the patient's doing. The reason that Pfizer is interested in this is that with new drugs in the market, they would like to have better measurements than the doctor's one-time occasional assessments. They would like to figure out how well the patient's doing at home. So if someone's deteriorating quickly over a week, they can capture that pretty rapidly. And they can also then tell the patient to up their medication if they need to, or maybe go to the doctor so that they can have a better outcome. So all of this data, all the algorithms we need to do all this work is hitting the limitations of the current quantum computer architecture and the way we have memory. And so we're in the process of thinking about how we can rationalize computing. One way we've been doing this is to look at the brain for inspiration. The brain is an amazing computer. It uses very little energy. It's massively parallelized. It can do transactions rapidly. So using the way the brain is structured, we've been developing a variety of techniques, both hardware and software solutions around what's called neuromorphic computing. trying to find chips that are designed like brain circuitry, using algorithms like deep learning to be able to apply that directly to the hardware. And we've been able to see ability to massively increase the amount of computing we're doing through this neural network chips. The other area we're working on is quantum computing. So this actually breaks the whole model of 0 and 1. Right? So we can look at states that are between 0 and 1 through quantum physics. We're looking at building computers and a whole set of devices that allow us to compute over quantum physics. And so this allows us to create algorithms that didn't exist before. And since it's 2016 here, we created the qubits on the cloud, so people could go and do computing on clouds. And so this is the room where the quantum computer sits. People are just working on improving it. It's something that if you wanted to work and create an algorithm for quantum computing, you could go and create an account on this at IBM Q and be able to then start driving algorithms and testing the algorithms out there. And we think this is, again, another fundamental breakthrough that's going to happen in computing. So blockchain to transform industries, and the neural network chips and quantum computing to create a new infrastructure for computing. So all of these things have helped us really to think about how we're going to advance our human capabilities, right? So we've gone from our physical limitations of traveling across oceans on boats to now having airplanes and equipment that can work on our behalf. We used to send letters to each other. We still get email, but now some of us just tweet and chat on Facebook or Snapchat or whatever it is out today. We've gone from being able to do calculations on small numbers to being able to do a massive amount of computing and look at the source of information. At the same time, all this technology, our brain has not caught up with it in some way, right? Our brain we still have all this massive power, but yet we haven't been able to figure out how to help us with all this computing. So there are things in the behavioral scientists know that can help us think about how to more effectively engage with artificial intelligence and with machine learning. One of them is that there are things that we can do very well, right? And there are things that would require us to be reflective about. The things that we do very well, the fast part of our brain, does all sorts of things such as identifying dangerous objects. There's a well-known study where a person is walking down a street and sees a stick. Well, think it might be a snake. The person actually doesn't step on that stick faster than they can actually see that's a snake. So our brain is wired in a way that we can't even consciously understand. So because we have those things built into our neural circuitry. But there are things, obviously, that, like education, that requires us to be very reflective and to process information slowly and to control it. So in many ways, this is the part where we need to understand how AI can help us to engage. There are a number of things that, unfortunately, as human beings, we make errors about. We discount the future. We want immediate gains. We see things like this. This looks like actually there's different colors, but these squares here are actually the same color. You turn on the pattern, turn on the light. So our eyes and brains trick us into thinking about things that where AI can actually help us to reason more properly. And this really brings up the idea that for us at IBM, that we're really not working on artificial intelligence. When we say AI, we're talking about augmented intelligence. How can we help people make better decisions faster, more accurately, more informed, instead of replacing human beings to do these things? We think that human beings are an important part of every part of life, right? Where there are places that computers probably do a very good job, but there are places where we would want us to be in charge and control. Things that involve ethical issues, things that require us to think about fairness, so forth. So this goes back to the healthcare system. Healthcare system, unfortunately, in the U.S. has been in the news quite a bit lately. We don't know where it's going to be quite yet next year, but it is really in serious trouble, especially in the United States. We have issues with, of course, financing our healthcare system, but we have issues of equity. We have issues of lack of knowledge about how things are going. And so when a patient comes to see their physician, it's really just a very fraught information, a fraught moment of person. Someone is coming in, they're having pain, they're concerns, and the physician is there to help try to alleviate that, to help them understand what they're having, to help them get better. Unfortunately, the way most physician-patient conversations happen is that by the time the patient leaves the physician's office, they forgot 50% of information that was told to them. By the time they get to the car in the garage, they've lost 80% of information. These are multiple studies that show this. Physicians, on the other hand, have about multiple questions popping in their head while they're asking patients information. And about 50% of those questions never get answered. So you have this huge issue where people forget what they were told, and physicians can't get some of the questions answered. And so there's why there's a lot of errors that happen in healthcare as a result of this, and misunderstanding. So we've been in the business of question answering for some time. Some of you may know we built this computer, Watson for Jeopardy, that was a global competition, and we did quite well. So if anyone, probably this is, somebody probably never saw the original one, but if you ever want to go back and look at 2011, when we put this computer into Jeopardy, we had to do a variety of things to make it work. First of all, we had to do voice to text and text to voice in rapid succession, right? So to be faster than two human beings, that's very challenging. Then we had to sort through massive amounts of information, right? We had all those questions of Jeopardy that had been asked of Jeopardy before, and we had to create a knowledge base that would be sufficient to be able to answer all that. So it gave IBM research work where Watson has developed an opportunity to get the best machine learning, the best information retrieval, the best interactive system in place at that time. Subsequent to that, of course, first of all, we did this before with Deep Blue, and we beat Kasparov in the chess game, and Google also did this with the Go game. Building machines that play games in a row is a great feat, but it doesn't necessarily get us to where we want to be. That is how do we help people. So I'm going to show you three different types of question answering and see if you can reach them. So these are all medically related. What is the first line treatment for acute urticaria? How do cells replicate? A 32-year-old woman with type 1 diabetes has had progressive renal failure. Her hemoglobin concentration is 9. A blood smear shows lymphatic lymphocyte cells. What is the most likely diagnosis? These are all different types of questions, right? That all have types of answers. Does anyone can distinguish between these three types of questions? Which is the one that's most likely in the Jeopardy format? That's right. That's the one that has a single answer, right? The next one has an answer. That's the answer, but it's not a simple answer. The last one requires us to get a context of this. So, yes, the first one is a simple question. You can just answer it with fact, just like we did in Jeopardy. You can answer just in context. When we did this within the Jeopardy, we were able to take information in the passage. The way the machine learning worked is that we looked at different parts of the source of information, location, the passage, the popularity of the passage, the source for lively typing, and we created positive and negative evidence for each piece of information. So we had a question like, Bolivia, Chile shares its longest land border with this country. The two top choices would be either Argentina and Bolivia. Okay? So based on these weights. But we can decide, based on each of these factors, which is more likely. So Argentina has the best evidence and the best answer for that. So we were able to weigh that to deal with the uncertainty in text. When we applied the same approach to healthcare, so we took a set of questions that called the doctor's dilemmas, which we trained our system on. And we looked at the accuracy of Watson for Jeopardy doing that. It was remarkably poor. So when we just took the system out of the box, as we had developed it and used it, we got about 50% of the questions right. When we added the content, more medical content to Watson for Jeopardy, they got 54% correct. And we did a few other things. We trained it, so we re-weighted those weights that we showed in the previous slides, and we added some functions to deal with medical information. We got to 77%. That's not great. That's like a medical student in first year medical school, right? So we want to do better than that. We have to figure out ways to do better. And then the team that I have in Yorktown Heights is working on that. So this one, the non-factor question with a complex answer, is actually done quite well by just putting the same question into Google now, right? So I can go to Google and I can say, how do cells replicate? And it'll come up with a source that gives me a fairly long answer, and it even tells me what other people have asked to run the same question, right? So in the second type of question, the web is doing well for us. It's able to answer these questions with structured information around the web to be able to get the information back. But this is the more challenging one. This is the kind of questions that physicians have when they're in practice. So they have a very complex case person in front of them. They have a number of pieces of data to deal with. They have a question that is, they have to make a decision to figure out the diagnosis is. And so this one is not something you can stick into Google. It's not something that the Watson for Jeopardy computer could actually answer. So how do we go about doing this? We have this user who has complex information need, has background context. It's not usually just one question, it's a series of questions, and they want to be interactive with the system. And so we have case examples that we've been working with. For example, the New York Times publishes a number of case reports in this series called Think Like a Doctor. And so this is a case of a child who has nighttime fevers. And so if you look at reporting this case, there's information about the patient, and then there's questions. Could this be cancer? Could this be tuberculosis? So you think about the differential diagnosis. And if you take this apart, you probably can't see it. You can see the things that are in information about the child, the things in red are tests that the child had, there's the things in green about context of where the child was, the medication the child took. So you can take this piece of this passage and break it down into pieces of information that are relevant to making the condition. And what we've done is we've built a way for a chatbot, which is shown on the left there, that you can feed the entire case. It will break down and pull apart all those pieces of information. It will go find resources and give you answers back here and help you look through that. And then you can weigh it. You can actually start, as you interact with the system, weigh pieces of information that is more accurate. So this is a way for physicians to quickly type in a question and get back level answers. To do this, there's a number of things you need to have from a machine learning and information retrieval and interaction perspective. One is you want to keep track of the context that the physician is asking the question. So if they tell you information about the patient, if they tell you some additional information, you want to keep all that in memory. So just understanding the context by which the question being asked is very important in answering the question correctly. Then there's just analyzing the question. What is the question they're trying to ask? Maybe the question is been formulated in a way that doesn't make sense. Maybe there are other questions that are relevant to that. So coming to understanding what the question is and drilling down the question is important. And then you need to make this seem intelligent, you need to have a controller in the background that's pulling apart the questions, taking apart the bits of information, and interacting with the person so that we're able to ask more questions about that. And then finally you can go and then do the question answering. So this system, this is what cases we've been built. We're testing that. This is rough screenshots of what it looks like with the chatbot on the right. And so this philosophy of this system is to be contextual, transparent, guidable by human being, collaborative, and proactive and anticipatory, right? Which is very different from how if we were just to go to Google, you just do a search and then get your results, or if you don't get your results, then you move on. This is a way to have the system be much more engaging, as I mentioned before. So the next part of this research is really trying to figure out how we can learn from the user how the system should best work, right? That the user, an AI system can get the answer wrong the first time, probably get the answer wrong the second, third time. But if you tell it that the answer is wrong by the fourth time and it hasn't figured it out, it's not doing any kind of learning, right? So you want to make sure that whatever feedback the users are giving the system's learning how to appropriately respond to that. And this goes to this very nice graphic here of where we are with machine learning right now. So the top part is the supervised machine learning approach. This is from an article in Brain Informatics from last year. So the top part, we get data, we build a model, we have people tell us what groups are in the data, for example, the clustering, and the model figures out how to, using this labeled data, figure out what the best algorithm is, right? So supervised learning, pretty standard. Then there are two examples of semi-supervised learning. You have a person who looks at the data at the beginning, tells us what data is relevant, so it's a feature extraction, tells us these are the features features that are most important. Apply some kind of algorithm to that. Individuals can look at that and see if the features make sense, and then someone can use it. And then there's this approach here, which is also unsupervised learning, which is that we do some feature selection, but whatever we get out of that is sort of discovered, right? So that's for the things that we don't know information about, sort of genomics, but we don't know which is the most relevant gene. We might apply this model and let the biologist then take the answer and test the experiment. But this is the model we need to move to, which is really interactive machine learning. We decide what features are important, but as the algorithm is being developed, it's constantly interacting with human beings, experts in the domain, who give it feedback and can give a lot of ways to change with the feedback. And this is where we want to be in healthcare, because we want physicians to be in the loop and try to understand how to make decisions. We don't want the system just to say, oh, this is just cancer or not cancer. We want them to say, okay, maybe you should order another test. If I had this test, I could reasonably understand and differentiate this condition from this condition, and that can help guide the physician. So this is where we're moving with our machine learning techniques, and it's really important to put the human back in this case. So I'm going to end there. I'll be open for questions. I'm very excited. I've been in research for about 14 months now. As some of the folks who were in the lab, some know I was previously a faculty member at Dartmouth, and then at Stanford before that, and I love working in the industry setting. I do almost the same kind of research, but I have many more resources, and I have all that diversity of activities that are going on from quantum computing, neuromorphic computing, blockchain that I can tap into our research projects. And so it's a fantastic place to be and to work. Thank you. Any questions?
So I guess I'm curious about the hyperledger and how permissions for that would look for you, customers, I guess, or people. How much control would the patient have for who gets access to their records? Would you put a chip on them so they get knocked out and in the emergency room you can still get access to them? Or what kind of ways would you allow people to get access to that data? I guess.
Right. So the situation where the patient is unconscious and can't give consent is always a challenge, right? So that is an ethical dilemma. We hope that they have somebody there, or they can find somebody who's a loved one who's giving consent. But some fingerprint, we're already at the point where fingerprint and face are already ways of securing our data. Not that we should utilize those, and patients still unconscious and still right. But there's always a scenario of break the glass, as we call it, where you have to get something and you can break the glass and find out what information is given. We've designed some prototypes already for this, and it's very simple. On the mobile app, it's just like signing in, right? It's just like signing in, and you see all the parties who have or want access to your data, and you permission them to do that. You can give them a time frame. You can have my data for 1 year, or when you see that they are not using your data, you can remove the permission from them. So from the user perspective, the permission is very simple. It's very simple. And pretty fail-proof, right? Because it's a double authentication and private key, public key, and all these things that we use now for verification. So does that answer your question? So we want to make this highly consumable. Right? It can't be, oh, I have to go and write down this smart contract myself and code it. We want to make it very simple. And in healthcare, the scenarios are very simple. Data's been collected on me. I collected my data. There are third parties that want to share the data. The data doesn't have to sit in one place. It can be distributed. But there's a link to each of those data points that I have on me. And when I permission a blockchain, I basically create a supply chain of all the data I have and who gets access to it. And then if I don't want them to have access to it anymore, then I can remove that from there. The biggest blocking aspect of this right now, not blocking it, but the biggest challenge right now is the fact that health systems, their own internal systems are not prepared for blockchain. As you know, IBM created the mainframe and promoted the mainframe, and now it's been working in cloud computing. We need a whole new infrastructure on blockchain that will enable that to happen. So we're still kind of limited right now when moving this out into places like healthcare where they spend a lot of money on IT, and it's still pretty old IT.
How do traditional learning models and related computational stuff change or perhaps start to break down when you move to neuromorphic computing or quantum computing?
It's a great question. So in quantum computing, they certainly are breaking down the way we program algorithms in quantum computing with not having a state where it's unknown, right? It's 1, 0 unknown state. You have to, and I'm not an expert in this, you have to write the algorithm in a way to allow you to deal with that uncertainty of that state. But by dealing with that, it actually verifies, or it allows you, it gives you a third state to store information in that way, right? You can store it as 1, 0, or unknown, and that increases the scope of what information is in. But then trying to interpret the unknown state is where the challenge is for that. Neuromorphic computing is simple because it's based on neural circuitries, and we already do a lot of things like with neural nets that are basically similar, supposed to be similar to neural circuitries. And now with deep learning and others, it's a matter of figuring out how to build these networks, cognition networks, reinforcement networks, and so forth, to mimic certain types of behaviors. Some of the work we've been doing with neuromorphic chips have shown that we can basically create vision through the chip, so we can identify objects, not on camera, but actually use the brain circuitry as we have in humans to be able to identify objects in space at that time. And this is pretty rough right now, so we can tell certain types of objects, but we are looking to try to build that even further. Right now, if you know about autonomous vehicles, they basically have a bunch of sensors on them, and they have some cameras and stuff. And those sensors are not very good. And it's, sometimes light changes or other things, it becomes very difficult for it to have the depth perception. So you really want a system that can really truly visualize like a human being or mammals and animals do, which is to have a sight field and have information object being processed very quickly. Any other questions? I will let you have the rest of your Sunday back. Is there more after this?
There's lunch downstairs for those of you.
Yeah.
Yeah, I think we're finally done.
Yes, congratulations for getting it this far.